Welcome back to the Deep Dive. Today we're tackling one of chemistry's real head-scratchers, the noble gases. For ages, everyone thought they were just, completely inert, didn't react with anything. But it turns out their story's way more interesting than that. There's some surprising chemistry hiding there, especially with one of them. Think of this as your step-by-step guide through this chapter. We'll break down the big ideas, make sense of it all.
It really is a fascinating bit of science history. I mean, finding these elements back in the late 1800s, it didn't just add boxes to the periodic table. It actually forced chemists to rethink bonding itself. We went from calling them rare, which wasn't always accurate, to inert and now noble. And noble kind of fits, doesn't it? Reserved, but not completely unresponsive. So our goal today is to walk you through that, especially xenon's chemistry. How do we get them to react? What do the compounds look like? How are they used? We'll try and paint a picture, make the structures clear even without diagrams in front of you.
Exactly. We'll start with the basics, like why are they usually so unreactive? Then we'll get into the really cool stuff. The compounds they do form, the uses, and the clever ways scientists actually make them. Okay, ready to dive into Group 18? Let's unpack this. All right, first things first. Group 18, we've got helium, neon, argon, krypton, xenon, and radon. They're all monatomic gases, so just single atoms floating around. And those names we mentioned, rare gases. Well, argon's nearly 1% of the air we breathe. That's hardly rare, is it?
Not at all. More common than corrosive, actually. And inert gases, well, we know that's not quite right either because compounds do exist. So the noble gases is where we landed. It suggests that, they're a bit standoffish chemically, but not impossible to persuade.
So what makes them so stable, so noble?
It all boils down to their electrons. They have a completely full outer electron shell. All the spots are taken, basically. For most, that's an ns²np⁶ configuration, 2s electrons, 6p electrons, just perfectly stable. And because of that full shell, they have really high ionization energies.
Meaning it's hard to rip an electron away from them.
Exactly. It takes a ton of energy. And the flip side is they have negative electron affinities. They don't want to gain an electron either because a new electron would have to start a whole new shell, higher up in energy. Not favorable.
Okay, that makes sense. And where do we find them? You mentioned argon in the air.
Right. Helium is number 2 in the whole universe after hydrogen, but on Earth. Pretty scarce in the atmosphere. It's just too light. It literally escapes Earth's gravity.
Oh, okay.
Argon and neon, though, they stick around. They're surprisingly abundant in our air. Then there's radon. That one's a bit different. It comes from radioactive decay of heavier elements in the ground. And it's radioactive itself. It actually contributes a fair bit to our natural background radiation exposure.
Right, I've heard about radon testing in basements.
Exactly. Now, if you look at the group as a whole, going down from helium to radon, you see trends. The atoms get bigger, obviously, radii increase. And as they get bigger, the melting and boiling points go up too because the weak forces between atoms get a bit stronger. But here's the crucial part. That first ionization energy, it decreases as you go down.
So it gets easier to remove an electron from the bigger ones.
Precisely. The outer electrons are further from the nucleus, less tightly held. And that's the key to why the heavier ones, especially xenon, start to show some chemistry.
Okay, so they mostly keep to themselves, but xenon is the exception. That's where it gets really interesting.
That's the one. Xenon forms a whole range of compounds, particularly with elements that really pull hard on electrons, like fluorine and oxygen.
What kind of compounds are we talking about?
We see xenon in oxidation states like +2, +4, and +6 typically. It forms bonds like XeF, XeO, even XeF₆, XeH, Xe. It can even bond to metals or act as a ligand in coordination complexes. It's surprisingly versatile. Krypton does a little bit, but much less. And radon. Well, it should be more reactive than xenon based on trends, but it's so radioactive, studying it is extremely difficult.
So the xenon fluorides are the big ones.
Definitely the classics. You can react xenon gas directly with fluorine gas, depending on the conditions, temperature, pressure, ratio of gases. You can get ZS, ZF, or S.
And what do they look like molecule-wise?
Okay, visualize this. EZF is linear, xenon in the middle, 2 fluorines sticking straight out opposite sides. SXeF, XeF is square planar, xenon in the center, 4 fluorines at the corners of a square, all in the same plane. XeF is trickier. In the gas phase, it's fluxional. Its shape is constantly distorting, kind of wobbling. In the solid state, it's more like a network of ions.
Wow, okay. Not simple shapes then for the hexafluoride.
Not at all. And then you have oxides, like COs and CO. Both are known, but be careful. They're extremely unstable, explosive, actually.
Yikes. Yep.
There are also personites, which have the iso or ion inside, and oxofluorides mixing oxygen and fluorine, like XeOR that's key-shaped, or isoair, which is a square pyramid shape. We even have some hydrides, like HXeH, and these things called clathrates.
Clathrates, what are those?
Imagine a cage made of water molecules, like ice, but with gaps. The noble gas atoms, argon, krypton, or xenon, can get trapped inside these cages. They're not chemically bonded, just physically stuck. It's actually a useful way to handle radioactive krypton or xenon isotopes safely.
That is clever. So it's amazing this whole family was missed for so long. Mendeleev didn't even predict them.
Nope, no gaps left for them. Their lack of reactivity meant they didn't fit the patterns he saw. The first clue was helium, seen in the sun's spectrum in 1868, way before they found it on Earth.
Hence the name helium from Helios, the sun.
Exactly. And the others followed. Neon for new, argon for inactive, krypton for hidden, xenon for strange. Radon, well, that's just named after radium, its parent element in decay.
And where do we get them from today? You said helium escapes Earth?
Right. Most terrestrial helium comes from radioactive alpha decay deep underground. It gets trapped in natural gas deposits. North America is a big source. The others, neon, argon, krypton, xenon, we get from the air. We liquefy air and then use fractional distillation, separating them by their different boiling points. It's a low-temperature process.
And in their pure form, just single atoms. But you mentioned dimers in the liquid.
Yeah, if you cool them enough to liquefy, the atoms can weakly attract each other through dispersion forces, forming temporary pairs or dimers. That's why their boiling points are so low. Those forces are really weak. And speaking of cold, liquid helium is wild. Cool helium-4 below about 2.2 Kelvin, and it becomes helium-2, a superfluid.
It's a superfluid.
Yeah, it flows with zero viscosity, zero friction. It can creep up the walls of its container, flow through microscopic cracks. It's bizarre stuff.
Okay, mine's slightly blown. So, beyond the weird physics, what are the practical uses for us?
Oh, loads. Helium, we talked about balloons, obviously safer than hydrogen, but the really big use is cryogenics. Its super low boiling point makes it essential for cooling superconducting magnets in MRI machines and NMR spectrometers. Huge for medicine and research. Plus, it's used to create inert atmospheres for growing perfect silicon crystals for electronics and in breathing mixtures for deep-sea divers to prevent the bends.
Right, the helium-oxygen mix.
And argon.
Argon's a workhorse, too. Great inert atmosphere for welding, preventing metals from reacting with oxygen at high heat.
Yeah.
Also used in incandescent light bulbs to protect the filament. And because it doesn't conduct heat well, it's used as an insulating gas between panes and double-glazed windows. Keeps the heat in or out.
Useful stuff. What about xenon? It's rarer, right? And more expensive, yeah. But it has niche uses. It actually works as an anesthetic, though cost is a factor. More importantly, its isotopes are amazing for medical imaging. Techniques like hyperpolarized XeNMR give incredibly detailed images of lungs, blood flow, even the brain, things traditional MRI struggles with.
That sounds incredibly powerful. And radon we mentioned as mostly a hazard.
Pretty much, yeah. The main concern is indoor accumulation from natural sources in the ground. Long-term exposure isn't good.
Oh, okay. But back to the good uses, lighting.
Absolutely. Their unreactivity is perfect here. Neon signs are the obvious one, that classic glow. But they're also in fluorescent lamps, powerful xenon flash lamps in cameras, and crucially in lasers. Helium neon lasers, argon ion lasers, krypton ion lasers, very important tools. The basic idea is you zap the gas with electricity, excite the atoms, and when they relax back down, they emit light at specific wavelengths.
So how did we even start making these compounds? You said they were thought to be inert.
The breakthrough moment was 1962, Neil Bartlett. He was working with this really powerful oxidizing agent, platinum hexafluoride, PTF. He found it could rip an electron off an oxygen molecule. Then he realized something crucial. The energy needed to remove an electron from oro was almost identical to the energy needed to remove one from xenon.
So you thought maybe PTF could react with xenon too.
Exactly. He tried it, and boom, he made the first noble gas compound, xenon hexafluoroplatinate. It just blew the field wide open. Suddenly, inert wasn't true anymore.
That's brilliant.
Yeah.
So that paved the way for making things like XeF₃.
It did. The direct reaction of xenon and fluorine is now the standard way. You just mix the gases and control the conditions. More fluorine, higher pressure. Specific temperatures generally lead to the higher fluorides like XeF and AVF. For XeF, you might use something like 300 degrees Celsius, 60 atmospheres pressure, and a 1:20 ratio of xenon to fluorine.
And I read about a simpler way for SS, the windowsill method.
Ha, yes, it actually works. You just need a sealed, dry glass bulb with xenon and fluorine, and then you leave it in the sun. The UV light breaks the ethyl molecules into reactive F atoms, and they attack the xenon. You get nice XeO crystals forming right there. Pretty neat.
Very cool. And XeO's structure is still kind of debated.
Well, its gas phase structure is definitely dynamic, fluxional because of that lone pair on xenon causing distortions. Solid state, it's more complex, involving XeO ions bridged by fluoride ions. It's structurally related to some other complex halogen-containing ions, actually.
So once you have these fluorides, what do they do chemically?
They're powerful oxidizing agents, first and foremost. They readily grab electrons. Their reactions often mirror other reactive halogen compounds. Think redox reactions and monathesis swapping atoms around.
Can you give an example?
Sure. XeF reacts with water carefully to make CS, swapping fluorines for oxygens, that's metathesis. Or ASEF reacting with water gives you back xenon plus oxygen gas, that's redox. The xenon gets reduced, water gets oxidized. They also react with Lewis acids, things that accept electron pairs. XeF plus antimony pentafluoride, SBFOs, gives you the salt XeF₆. It forms a conterration.
And Lewis bases, too. Things that donate electrons.
Yep. XeF can react with a fluoride ion, F, which is a Lewis base, to form the XeS anion. That one has a cool pentagonal planar shape, 5 fluorines in a pentagon around xenon, with lone pairs above and below. There are even bigger ones, like X and the XeO known.
Wow. So these fluorides are like starting points for other xenon compounds.
Exactly. They're gateways. You can use them to make compounds with egg-ion bonds, for example. You might use nucleophilic attack or react them with a Lewis acid first, then add something else. Lots of synthetic strategies branch out from the fluorides.
Okay, what about the pure oxides, like Daisho? You said they're unstable?
Highly unstable, yes. They're endergonic. You have to put energy in to make them. They don't form spontaneously from xenon and oxygen. That tells you they're not thermodynamically happy. You generally make them by hydrolyzing the fluorides. XeF plus water gives XeO. Handle with care. It's a powerful oxidizer and, yeah, explosive.
And the personates. XeO₃. How do those form?
Those come from Z. If you have the Z-oxoanion HXeOL in a basic solution, it can disproportionate. That means some of it gets oxidized to XeF, the personate ion, and some gets reduced all the way back down to elemental xenon gas. So Z basically reacts with itself to form Z and XeO.
And personates are more stable.
Relatively speaking, yes. They're usually white crystalline solids. The CO ion itself has a nice symmetrical octahedral shape. Xenon in the middle, 6 oxygens around it at the corners of an octahedron. VSEPR theory predicts that nicely. If you take a personate salt, like barium personate, and react it with strong sulfuric acid, you can generate XeO gas. But again, very unstable, explosive stuff.
And the oxofluorides are mixtures. XeO₃, XeOL.
Right, combining both oxygen and fluorine bonded to xenon, like azeose, T-shaped, XeO₃ square pyramidal. There's even an XeO₃ ion, pentagonal pyramidal, formed if you dissolve fluoride ions in XeO₃.
Okay, shifting gears a bit. Xenon insertion compounds. And this missing xenon idea. Tell me more about that.
Right, the missing xenon problem. We find way less xenon in our atmosphere than we expect, based on the amounts of other noble gases like Krypton or argon relative to their cosmic abundance. It's off by like a factor of 20.
So where did it go?
The leading theory is that deep inside the Earth, under incredibly high pressures and temperatures, xenon might actually react with minerals. It could form stable insertion compounds, maybe substituting for silicon and silicate rocks, effectively locking it away in the Earth's mantle or core. It's a fascinating possibility explaining the atmospheric depletion.
That's wild. Trapped in rocks deep underground.
Potentially. And related to insertion, we have these HEY compounds, noble gas hydrides like HXeCl, HXeOH, even HXeOXe, the smallest molecule with 2 xenon atoms. They're usually made by UV photolysis of precursors frozen in solid noble gas matrices at very low temperatures. Highly unstable, but they exist.
And actual xenon-carbon bonds. Organoxenon.
Yep, that was another big step, first reported in '89. We can now make compounds with direct Xe bonds, often starting from X1 or hetero. One method involves reacting them with organoboranes. The xenon kicks out the boron.
Are they stable?
The Z ones, not very. They tend to decompose above maybe -40 Celsius. But there's this cool XeO ion 2 xenon atoms bonded together, which has the longest bond known between identical main group elements, really stretched out. For Sayre organocompounds, stability improves if the carbon is part of an aromatic ring, especially one with electron withdrawing groups like fluorine attached. That helps stabilize the Xe bond.
Okay, one more really weird one. Noble gases as ligands. attached to metals.
Yeah, coordination compounds, known since the 70s, actually. The first stable one characterized was Oxofluorides, a gold ion surrounded by 4 xenon atoms in a square plane, stable up to about -78°C, made in a special solvent mixture.
How does that even bond?
It's a weak interaction, but real. We also see transient ones, like metal carbonyls with a noble gas attached, MCOE, where M is chromium, molybdenum, or tungsten, and E is argon, krypton, or xenon. These are usually trapped and studied using matrix isolation, freezing them in solid argon at like 10 Kelvin.
And there are trends in stability.
Definitely. Tungsten forms the most stable ones among those metals, and xenon forms stronger bonds than krypton, which is stronger than argon, matches the polarizability trend. The bonding involves interactions between the noble gas p orbitals and orbitals on the CO groups. Subtle stuff. Some rhodium complexes have even been made in supercritical xenon.
Amazing. So just quickly, what about krypton and radon chemistry? It's more limited.
Much more limited for krypton, mostly just Kr. Radon should be more reactive due to lower ionization energy, and there's evidence for things like R and F salts, but studying it is hampered by its intense radioactivity. It's just too dangerous to work with easily.
And Kr is itself.
Krypton difluoride, made using electric discharge in a cold KrF mix. Like ECS, it's linear, but it's colorless, highly reactive, and only stable at very low temperatures, much less stable than a geos. We even have argon hydrofluoride, made by UV irradiation in solid argon, stable only up to about 27 Kelvin, a real achievement. And the clathrates we mentioned are Kra, trapped in water, or quinol cages. Helium and neon are too small, they just slip out. There's even speculation that clathrates might explain why krypton and xenon seem depleted on Saturn's moon Titan.
And noble gases inside fluorines.
Yeah, endohedrofluorines.
Yeah.
Literally trapping he or Ni atoms inside the CRO buckyball cage, not chemically bonded, just physically encapsulated.
The helium. Still basically unreactive.
Pretty much the king of unreactive. Apart from being trapped or some fleeting ions seen in experiments, no stable neutral helium compounds are known. There are theoretical predictions, like for HEBIO, but nothing isolated. It really holds onto its electrons tightly.
So, wrapping this up, we went from thinking noble gases did nothing to finding this whole rich, complex chemistry, especially for xenon. It really challenges that old inert label.
Absolutely. It shows how understanding atomic properties, ionization energy size, electron affinity helps predict and explain reactivity, even where you don't expect it. We've seen xenon form fluorides, oxides, hydrides, bonds to carbon, bonds to metals. It's incredibly diverse, and it highlights the clever techniques chemists use low temps, high pressures, matrix isolation to push the boundaries and study these fascinating, sometimes fleeting molecules.
Yeah, it's a great story of scientific discovery. And that missing xenon idea makes you wonder, doesn't it? What other weird compounds might be out there? Maybe in extreme places, other planets, deep Earth, things we haven't even imagined yet.
It definitely leaves the door open. There's always more to find out.
Well, that's all the time we have for this deep dive. Huge thanks for walking us through that. Until next time, from all of us here at the Deep Dive and the Last Minute Lecture team, thank you for listening.